So looks like about half of you are not loving this icy weather. I have to say, I agree with you. I would totally be at home today, but since, as I pointed out yesterday, my husband is also a teacher working via Zoom, and he has a very loud voice. It makes it very difficult for both of us to Zoom at the same time. So I decided to come into my office. Now you can often tell the state of my brain by the messiness of my office. And at the moment it is so messy that I am just putting a background screen on because I don't want you to see all the junk in my office. So hopefully I'll have a chance at some point to clear my mind and clear my desk. So let's get started here. The first thing that I wanted to do was to, oh, I know what I want to do first. We had looked at that, those hand warmers yesterday, and where did I put that paper? All right, so we had these two different kinds of hand warmers. And I had written down that the mass of this hand warmer, oops, getting in front of my face, was 169.9 grams. And I weighed it after class, and I weighed it twice, and the average of the two times was 169.9. So basically it didn't change its mass. The one was 0.1 higher and 0.1 lower. So it was just like a 0.05% difference, but that's really more the balance than it is the hand warmer. So if you were thinking that this one wouldn't change mass because of conservation of mass, you were right. Everything is sealed inside of there, and that is accurate. So with this one's a little bit trickier because conservation of mass says mass shouldn't change, but all of our reactants aren't in here. So since some of the reactants, that is oxygen, were outside to begin with and weren't being weighed, hopefully you were thinking maybe the mass will go up. So originally the mass was 21.7 grams. And then after class, I weighed it at 22.2 grams. So only a small increase, but that's 2% compared to the 0.05% of the other one, a little over 2% even. So yes, the mass did go up on this one. I haven't had a chance to weigh it again today. It might weigh more now that it's had more of a chance to complete its heating process. Okay. Okay. All right. So we were trying to find moles and molarity. So you're going to want to, again, have a calculator handy and have some numbers handy. If you don't have your periodic table by your side, remember that hydrogen is 1.01 grams per mole. That's 1.01 grams per mole. Carbon is 12.01 grams per mole. So carbon is 12.01, and oxygen is 16.00. So oxygen is 16. All right, so things that we are looking for when we are trying to do molarity. We want to make sure that when we're plugging things into a formula that we have the right units. So molarity needs the units of moles and liters, but sometimes instead of giving you moles and liters, I'll give you moles and milliliters. And so you'll need to change the milliliters to liters. Sometimes I might give you grams and milliliters, so you would need to change both. And sometimes I might just give you grams and liters, so you would only need to change the grams. So we're going to go through a couple of examples of those, and I'll give you a chance to try some on Top Hat by clicking them in. All right, so first example, and this isn't one for you to click in on. What is the molarity of a 750 milliliter solution made with 1.22 moles of citric acid? So we're first going to check our units, and we were given moles, which is great because that means we don't have to change anything there. We'll just leave it in moles. But we were given milliliters. So we're going to have to convert milliliters to liters. And that's going to happen by dividing by 1,000. So we take our 750 milliliters, and if we want to set it up for unit analysis, we're going to have 1 liter divided by 1,000 milliliters, because those are equivalent. And we'll get 0.750 liters. Or you might just remember we're going to move that decimal over to the left 3 places. Okay, so now that we have liters and moles, we can plug things into our molarity formula. So molarity is moles divided by liters. So we'll put in 1.22 moles divided by 0.750 liters. And when we do that, we get 1.63 moles. Okay, so before I go on to your question that you're going to do on Top Hat, does anybody have questions about what we did here? You can just unmute yourself and ask your question, or you can use the little raise your hand feature. Okay, so I'm going to stop attendance. I think you've all had a chance to finish that. And then we are going to go on. And so now you're going to have very similar setup. What is the molarity of a 350 milliliter solution of brine? So brine is basically salt water. And it contains 0.55 moles of NaCl. And NaCl is salt. All right, so we're going to do this the same way. We have moles of the sodium chlorides. We don't have to do anything to that, but we do need to change the 350 milliliters to liters. So I'll give you a chance to try that. And I'm going to add some time to this. And then our formula for molarity is moles divided by liters. All right, we've got about 20 seconds left here. Okay, so let's see what people answered. Got a lot of answers in the 1.5, 1.57-ish range. And I think I calculated 1.57. So it gives me the ability to give a percentage range, and that's what it did here. That's why we've got so many decimal places. We don't really need that many. People who had the 0.00157, I think your problem was you just divided by the 350 instead of dividing by the 0.350. So that's the issue there. And then I think some people just put in the liters. Okay, so we're getting the hang of this slowly but surely. Now, those of you that didn't answer, if you don't have a calculator now, do try and do these problems after class when you can find a calculator, because on your test next week, you're going to need to know how to do those. All right, so let me give you a correct answer. Okay, so second example. So this one's a little more challenging. What is the molarity of a solution made from 25 grams of salt, NaCl, in 2 liters of water? So in this case, we have the liters, but we need to find moles of salt. So we are going to find the moles, the molar weight of salt. So that's NaCl. So we're going to take 22.99 plus 35.45. Now, somebody unmute yourself and tell me, where did these two numbers come from? Where did I find 22.99 and 35.45?
The periodic table.
Excellent. Yes. So we're just going to find those symbols on the periodic table. add those two numbers together, get our 58.44. And so then once we have the molar mass, we're going to find the moles by taking mass divided by molar weight. And I did put these equations on the chapter 3 page on Canvas, so you should be able to find them. So I'm going to take my 25 grams divided by the molar weight and get 0.43 moles. So that's the number of moles of salt, but that's not the molarity of the solution. I know it's confusing that we have all these terms that are so similar to one another, but we've only done the problem halfway. Okay, so the next thing we need to do then is to go and find the molarity by taking moles divided by liters. So this is part 2 of the problem. 0.43 moles divided by the 2 liters gives us 0.21 moles per liter, or sometimes we just use that capital M to mean molarity. Okay, so this is an example of what we're going to do. And I know some of you are writing this down as we go, so I don't want to rush too quickly as people are jotting stuff down. I'm going to give you a few seconds to get caught up. And the problem that we're going to do is going to be very similar to this. And what I'll do is I'll actually break it into 2 questions. So first I'll ask you to find moles, or first I'll ask you to find, I forget whether it was moles or molar weight. And then second, I'll ask you to find molarity. All right, so I'm going to move on to the question. So we need to find the molarity of a solution of 3.5 grams of acetic acid. So this is what's in vinegar, and it has the formula C2H4O2. So yesterday when we looked at it, I kind of spread it all out. That gives more of the structure of how the molecule looks. Here I'm just giving you the elements, so all the carbons and hydrogens and oxygens are together. So we're going to have to add those up. And remember, I told you that carbon is 12.01. Hydrogen is 1.01, and oxygen is 16 on the dot. All right, so the first question I'm going to ask is, what is the molar mass of the acetic acid? All right, so let's see what we got. Okay, kind of a range here. Okay, so some of you jumped already to moles. So we were just looking for the molar mass here, but if you found moles, congratulations. So what we were looking for is probably something right around 60, should be 60.05. So we have 2 carbons at 12 is 24. And 2 oxygens at 16 is 32. So 32 and 24 would be 56, I guess. Yeah, 56. And then add 4 more for the hydrogens, that would give us 60. So the correct answer is this 60 range here. So it looks like some people need some practice adding those things up on the periodic table. So you might want to look into, I'll see if I can set up a practice assignment on Canvas over the weekend that you can work with on that. Okay, so everybody write down 60 or 60.05 as their molar mass, because you're going to need it for the next part of this problem. Now, I didn't ask the intermediate, I probably should have asked the intermediate of what is the number of moles of acetic acid. So before I go on to the final question, maybe we should just calculate that. So we're going to take the grams, the 30 or the 3.5 grams, and then we're going to divide that by 60. So go ahead and plug that into your calculator. So you remember I said the people that were in this lower range, they had probably already done that. So you should have something about 0.058 as the number of moles of the acetic acid. Okay, so jot down 0.058, or if you use 60.05, you might have gotten 0.057. Either way is fine. And plug that into your calculator for the moles for the next question. So let me move on. So follow up. Now we want to find what's the molarity. So we're going to use our 0.05 moles and we're going to use the 1.5 liters. 20 seconds left here. All right. So let's see the responses. So we should have gotten somewhere around 0.038. Looks like a couple people missed a decimal or missed a zero when they were plugging some things in here. So you probably did this right. If you got the 0.37, you just moved the decimal or delete as a zero or something when you were doing that. So our correct answer is 0.037 or 0.038, maybe 0.039, depending on exactly which numbers you put in. Okay, so it looks like we'll probably need to do a little bit more practice with this again on Monday. Let's see. Jalen says her questions are not popping up on Top Hat like they usually do. Is anybody else having that problem? Okay, so Grayson is too. Okay, so what I'll have you do is if you can't get it to pop up on Top Hat, you should be able to see it on your Zoom screen. You can type your answer into the chat, and that way I can see what you're doing and, you know, get a sense of, are people getting it correctly? If you want to send it so only I can see it, at the bottom of the chat where it says 2, you can change everyone to just me, and then I'll see your answer, but nobody else will see your answer. You know, I don't care if you share it with everybody, but, you know, maybe you don't want everybody to see your desk, so that's fine. I know that somebody told me that when they logged into Top Hat with a different email address than their original login, that made that kind of a difference. So you may check and see with, you know, how you registered at Top Hat and how you're currently logging in. So if you're using your phone and your phone uses, say, Yahoo email, that might make a difference in whether or not it pops up. But if this is the first time that that's happening, I'm not sure, and I'll have to check with Top Hat. Okay, so thank you for bringing that to my attention. All right, so I think that's the end of this. End here. All right. So what I want to do is I want to go back to our discussion of moles and molarity and talk a little bit about what's happening when we dissolve things and what the limits to dissolving things are. So presenting another slide. So I'm going to have to unassign this. If it disappears from your Top Hat, that's because I've forgotten to reassign it. So just send me an email and say, hey, Dr. Knapp, I can't see that presentation. Okay, so we have a picture here up above. This is kind of a molecular view of what might be going on. Now, of course, we can't actually see molecules, and molecules don't really have colors because they're much smaller than light waves, so they can't have colors in and of themselves. But the grayish blobs that kind of look like Mickey Mouse are supposed to be water molecules. And then we've got an orange ball with a plus and green balls with a minus. And so this is supposed to be what sodium chloride might look like if it were dissolved. So the sodium is positive. It's an ion. What do we call a positive ion? Somebody unmute yourself and tell me what a positive ion is called.
A cation?
That's correct. So notice how all of the big blobs of the water molecules are pointed towards the sodium, while the little ones are kind of pointed away from it. So the big one is the oxygen and the little ones are hydrogen. So the hydrogens are a little more positive, the oxygen is a little more negative, and that's because of electronegativity. We've talked about that before. So oxygen along with nitrogen, very, very electronegative. And so they're going to have more of a negative charge and point towards the sodium. And so you get this, what's called a hydration sphere, but just sort of a little sphere or circle around the sodium that's all water, and there's no chlorine in it. So you kind of have to go out a couple layers of water molecules to get to the chlorides, and then the chlorides have all of the hydrogens pointed at them. So when we say something is dissolved, what we mean is that each individual particle is completely separated from the other particles. The sodiums are not touching the chlorides, and they're also not touching sodiums, and the chlorides aren't touching other chlorides. All of the salt particles are completely separate from one another. So if something is dissolved, the water, which is usually our solvent, completely surrounds each molecule or each ion of solvent, or of solute rather. So there's a limit to how much we can do this, right? We don't expect to put 1 drop of water in an entire salt shaker and expect that to dissolve all of the salt. So that limit of how much we can actually get to dissolve in there is what we call solubility. And once we reach the limit, we say the solution is saturated. Okay, so what is going to cause some limits? So things that are important, mostly in chemistry, we start talking about polarity, which we've already talked about, like dissolves like, and charge. So polar things will dissolve in water, non-polar things will dissolve in oil, and things with a charge on it generally dissolve in water. But if we have really, really high charges, like if instead of a +1 and a -1, if it was a +3 and a -3, then that would be really hard for the water molecules to kind of wedge their way in between the ions. And so that just wouldn't dissolve because they're just so tightly held to each other in the first place. So the charge matters and the polarity matters. What about size? Well, if you look at something like a cotton shirt, that's made primarily of starches, might be some fibers, so cellulose, and might be some amylopectins and things, but they're basically starches which are in what food group? Is it carbohydrates, proteins, or lipids?
Proteins.
Okay, so proteins have amino acids as kind of their base thing. For starches and fiber, they're going to fit into carbs. So, so carbohydrates tend to be very polar because they have all of those alcohol groups. Remember the OH that sticks off all over the place? Those were alcohol groups. And that makes them very polar, and that makes it also soluble in water. And we also introduced that term earlier in the week, that it has hydrogen bonding. OH is a very hydrogen bonding type of situation, which is kind of like superpowered polarity. So you might think that something that's made of starches and fibers would be very soluble in water, but we can wash our clothes and they don't dissolve. So part of what happens is that when we have a really, really, really big molecule like polymers, the chain is just so long that it's really too hard for the water molecules to completely surround all of the polymer, all of that chain. And so because of that, we can't dissolve things that the molecule is just too big to do that. So size, polarity, and charge are going to affect that. The slideshow from PowerPoint, the background that I chose has these home and arrow buttons on them, which work if I'm in PowerPoint, but on Top Hat they don't. And so I keep wanting to go over and click on those buttons, but it's not going to work. So I have to click down here at the bottom. Okay, so saturation, what's this limit? Saturation, the definition would be the maximum amount of a solute that would dissolve in a solvent. And so usually for us, that solvent is going to be water. If you go on in chemistry and do other stuff, there's lots of other solvents you could talk about, but for us, it's water. And so that is generally based on a concentration. So we know that we can do that concentration based on molarity, what we've already calculated. But a lot of times if you look up what that concentration is or what the solubility limit is, it's going to list how many grams of sugar can I dissolve in 100 grams of water? How many grams of salt can I dissolve in 100 grams of water? And so if you look in comparison here, sugar versus salt, we can dissolve a lot more mass of sugar in water than we can salt. But remember that sugar had a molar weight of over 300. So we calculated that yesterday, it was 342. Salt we just did today, that was 58, so almost 60. So even though we have a lot more mass, because the mass of each particle is greater, it ends up being about the same number of particles. Okay, so there's an unusual situation that we can have called supersaturation. So supersaturation is when we get more dissolved than is stable at a given temperature. So usually we say, what's the limit? And we get to that limit and we just can't dissolve anymore. But the amount we can dissolve changes with temperature. And for a lot of things, if we raise the temperature, we can dissolve a little bit more. So I might be able to dissolve, let's see, what did it say for sugar? It said 200 grams of sugar close to room temperature, but I can maybe go to 300 grams when I'm near the boiling point. And that number increases the higher the temperature is. But then if I start to cool it back down again, I shouldn't be able to have that much still dissolved. So theoretically, as it cools back down, I would start getting some of the material to undissolve. So the chemistry word for undissolving is precipitating. So we would have the sugar crystals start to form and it would precipitate out of the solution. But if you cool something very, very slowly and you don't look at it and you don't touch it and you don't let your dog bark and you don't let your cat walk by the counter, as it cools down, those molecules don't drift close enough to each other to start forming crystals. And so it will stay dissolved. So the hand warmer that we looked at yesterday is actually that situation. I meant to bring another one, but my daughter decided to set it off last night at the dinner table, and so I haven't reset them yet. But that's a supersaturated solution of sodium acetate. We bring it to a very high temperature, boil it, and all of the crystals dissolve. And then as it cools down to room temperature, it hasn't had enough disturbance in order for the crystals to start to form. So when we have a situation like that, it's what we call metastable. So meta kind of means in between. And so it's sort of stable. It's stable because I can have this pack, just kind of sitting around and it's not gonna spontaneously start to crystallize, but it doesn't take too much to get it going. So one thing I can do is I can add a crystal of really anything, but usually it's best to use the same material. So if I took a crystal of sodium acetate and dropped it in there, then the nearby molecules would say, oh, we can start forming crystals, and they would all start precipitating out. So that's one way I can set it off. But of course, I can't really get a crystal inside that sealed pouch. And so that's why there's that little metal piece there. So when I bend that little metal piece, that creates just a little bit of heat, a little bit of energy, and that's just enough energy, what we call activation energy, just enough energy to start the crystallization and set it off in that local place. And once I have one little crystal, all the nearby ones start going and we start spreading out the crystallization. So why do we care about this? Well, this is actually really important in cooking, especially in candy making. And we'll talk more about candy making on Monday. And we might get a little bit into it today. But with candy making, whether you have something form lots of crystals really quickly, or you have something cool down very slowly so that it doesn't form crystals, or whether you cool it so rapidly that you can't get any crystals, makes a difference in the texture. We can get teeny tiny crystals, or we can get medium-sized crystals, or we can get no crystals at all, just a glass blob. Well, it's glass in the chemistry terms that it's not a crystal. It's not really like turning into glass. Okay, so terms to know. We need to know what saturation is, and we need to know what supersaturation is. I'm going to try not to overtax the mathematics of your brain. So we're not going to do calculations in terms of this grams per 100 grams. We'll stick with molarity for everything. So we just have one thing we're looking at and not try and do 100 different ways to calculate stuff. But if you see a table that talks about it, this is what it's referring to rather than per liter. One reason it does that is that we can dissolve so much sugar into water. You can see gram wise, it's twice as much sugar. Well, when I mix that much sugar into water, I no longer have 100 milliliters of water. I have a lot more. It's probably going to be closer to 200 milliliters of the mixture. And so I change my volume. And so that's why we use these different units here. But again, I'm not going to worry about doing calculations with that. All right, so who eats the most chocolate? You might think Americans do, because Americans really just always tend to be on the bad end when it comes to food, that we just eat too much of the wrong things. But Switzerland, Germany, these are big chocolate eaters. So this is how much chocolate per capita or per person, capita is like head, per person each year. So each person in Switzerland on average eats almost 19 pounds of chocolate. Now this data is probably about 4 years old, but we would assume it'd be pretty similar. And let's see, for the US, we have to get down to, we're 9th on this list. So we're only consuming about 10 pounds of chocolate a year. And that's with us having Valentine's Day and Halloween and Christmas, which are all big chocolate holidays, not to mention the fact that, people just tend to love eating chocolate. So we got all over Europe, people love to eat chocolate, and in the US, we love eating chocolate. I noticed that there's not even Canada on this list. And Australia is on this list. We got one place outside of the US and Europe eating chocolate, and they out eat us in the chocolate. So very popular food. What's in the cocoa bean? So we have the cocoa bean is where the chocolate comes from, and it's got lots of different things in here. Now these kind of look like scary words, but we can sort of break these things down. At the bottom, we have elements. So we have iron, magnesium, phosphorus, potassium, and copper. So these are going to be our minerals. So many of these are really important for just our everyday living. We need iron in our blood in order to help us use oxygen. Phosphorus helps to build our DNA. Potassium helps us to send signals through our nerves. So all of these can be used in various ways. Copper is more of a trace element. We only need just a teeny tiny bit of it. The next category, polyphenols, are special chemicals. We'll get to those in chapter 5, I believe. But these are things that you sometimes hear about, oh, chocolate is so good for you. It has these things that are antioxidants. So these are the things that help with like blood pressure and help you live longer and whatnot. So these are actually good chemicals to have in there. And then up here, arginine, glutamine, and leucine, those are amino acids. So remember, amino acids make up our proteins. So this is our first big chunk of the cocoa bean. It's a little over 10% protein. We do have a little bit of protein in our chocolate. Good to know. Carbohydrates. So we have carbohydrates, but only a teeny tiny bit of sugar, and most of that is fiber. So remember, fiber is cellulose, and that we cannot digest. So this means if you were to eat a cocoa bean, good fiber, but it also means that it's not very sweet. So if you've ever, a lot of people when they're kids, they might ask their parents, oh, can I try that baker's chocolate? It's chocolate, looks good. And maybe you have cocoa powder or something like that at home, and you try it and it just tastes terrible. It's so bitter. And that's because it doesn't have any of the sugar in it. Now, if you don't have parents that were much of bakers, you may never have tried it. But if you ever buy a container that's cocoa powder instead of chocolate mix, it's not going to have sugar in it, and it's not going to taste nearly as good as regular chocolate. Some people like it pure. I'm going to say it doesn't taste very good. Okay, so that's about 30% fiber. So far, fiber and protein, that sounds pretty good. And then we've got 54% fat. So half of the cocoa bean is made up of fat. And so you'll see in here oleic acid, stearic acid, and palmitic acid. These are what we call these are what we call fatty acids. So we've talked about those as kind of the building blocks of fats. And so these three fatty acids make up most of it, and there's a couple of other fatty acids that are in there. And stearic and palmitic acid are what we call saturated fats. So you may have heard that as, oh, saturated fats aren't so good for you. There's a little bit of evidence that's more recent that fatty acids aren't saturated acids are not as bad as we thought. But there's a lot of evidence that unsaturated fats like oleic acid, unsaturated fats are better for you. And that's primarily because instead of being solids, they're liquids. And so if you imagine these fatty acids in your bloodstream, the ones that solidify are the ones that can clog up your arteries, but the ones that are more liquid can move more easily through your arteries. So that's kind of the main advantage of having the unsaturated fats. And there are some other advantages too. Okay, so chocolate has fats in it, but it also has these other things in it. So one of the things that is kind of counter to the thing that dark chocolate is good for you is that the darker the chocolate, the more fat there is in there because there's less sugar taking up that percentage. So if you're trying to have a low fat diet, unfortunately, chocolate isn't the best way to go. All right, so this is what a cocoa bean pod looks like. So the big thing is the pod, and these individual things are the beans. And my understanding is that this whitish part is the cocoa butter, the fatty part. And you can actually get that separate from other things. Sometimes it's used kind of like a lotion is, that it can help to make your skin less dry and to soothe stretch marks and things like that. So we have to get this thing out of here, and then we have to chop it all up into the little cocoa nibs that are useful. So they separate the cocoa butter from the solids. The solids can be powdered. So if they grind it up enough, we'll use it for mix it with sugar and make our chocolate milk mix, or we'll mix it with, just leave it as a powder for baking. And then we can also mix it with the cocoa butter with sugar and other ingredients to make white chocolate. So white chocolate is cocoa butter without all of the fiber and the proteins and those kinds of things. So that means that white chocolate doesn't have those chemicals that are supposed to be really good for you. The antioxidants are really good for you. But it does have the fat. So kind of the disadvantage of white chocolate. What we'll find out later is that this is why dogs can eat white chocolate, but they can't have other chocolate, because the stuff that makes it good for us is something that is dangerous for dogs. So white chocolate, okay for dogs. Dark chocolate, milk chocolate, not okay for dogs. White chocolate, less benefit for us. So there you go. So eating chocolate, the candy type chocolate, generally has a higher percentage of fat. So they might add a little bit of extra cocoa butter in order to give it a nice texture and help it to melt a little bit better. All right, so you maybe have seen chocolate that looks like this. It kind of looks like it's molding. That's actually not mold, it's just fat. So remember, we've talked about emulsifiers, where fat dissolves in nonpolar things and sugar dissolves in polar things. And so we have added to chocolate, usually it's called lecithin, but some kind of an emulsifier to help them stay mixed together. So two things can happen. One, as you maybe are melting chocolate just a little bit and then refreezing it, melting it and refreezing it, they can start to separate from one another. But the other thing that can happen is that it can melt and then refreeze at different temperatures. And depending on the temperature that the chocolate refreezes at, it might form these blooms, or it might look like the really good looking shiny chocolate. And that depends on how big the crystals are as well. So this is basically just normal chocolate where the fat has crystallized in an unappealing way. But if I took this Hershey bar and melted it all, stirred it all up, and then put it back into the Hershey mold, it would look fine and it would taste fine and it would be just like any other chocolate. But these tend to have more of a crumbliness to them. You know, normally you would stick a piece of chocolate in your mouth and it just melts in your mouth. Very smooth texture, but this would be more like it just crumbles into little pieces. So that's what's going on there. All right. Okay, so I've been talking for a few minutes. We talked about cocoa butter being a fat. Fats are nonpolar, so they're going to have a hard time mixing with what? All right, we've got nearly everybody in here. Okay, so let's see what people said. Most people said sugars, and that is correct. So it will have a hard time mixing with sugars. Anything that is fat or butter is going to mix well with other fats. So nobody picked milk fat. A wax fits into that same category with fats. Waxes are also non-polar. So you could probably take your candle wax and mix it in with other kinds of fats fairly easily, especially if you got it to melt a little bit. But it's not going to mix very well with sugar. So that's why we have that lecithin in there, that emulsifier, keyword emulsifier, to help keep them mixed well. All right, so we were talking about the different kinds of fat crystals. So the fats, and I usually, oops, didn't want to do that. I usually have kind of examples of this that I can show you in class, but since we're doing this over Zoom, I don't have this as well. But fat crystals, because fats are these really long molecules with these long chains, there are several ways they can kind of come together depending on how those chains are arranging themselves. And so the different ways they can come together are the 6 polymorphs. So sometimes one of the chains kind of goes up and the 2 go down. And so it sort of looks like a letter H or like a chair. And so those can kind of stack together in a certain way. Sometimes they all spread out, sometimes they ball up. So these different shapes melt at different temperatures. And so when you have a chocolate candy or chocolate making factory, what they're going to do is they're going to keep all of the chocolate right about the melting point of phase 5. So right around 33 degrees. Now, remembering how temperatures in Celsius are different from temperatures in Fahrenheit, 33 degrees is above room temperature. Room temperatures in my office right now is probably about 20. It's kind of chilly. Usually we say room temperature is 25. That's a little warmer than Americans like it. But your body temperature should be about 37 degrees. So 33 degrees is below your body temperature. So this is why chocolate will melt in your hand if you are holding on to it. So they're going to keep it right around there. So it's only going to form that one kind of crystal. And when they do that, those crystals come together very, very nicely into the picture on the right-hand side, what's called tempered chocolate. So if you have a chocolate bar that looks shiny like that, when you go to break it, instead of bending in sort of a wah, wah, wah kind of pathetic way, tempered chocolate will give a nice snap to it, and it'll have that shininess to it. So that comes from crystallizing at a particular temperature. Now, you don't need to memorize what phase it is or what temperature it is, but it's just because it's forming one particular kind of crystal that gives the most pleasant mouthfeel and gives the most pleasant visual appearance. So as we heat it, the fats might recrystallize, they might separate from the sugars. And as they separate from the sugars, then that's how we can get those fat blooms. If we take this tempered chocolate and say, leave it in our car. And so it warms up in the sun, it starts to melt a little bit, and then it cools back down, and then it solidifies, and it does this over and over again. So then we can get the other polymorphs, the other phases. All right. So let's see, the crystallization temperature for tempered chocolate is 33 degrees Celsius. And where is that compared to other familiar temperatures? So let's see if you were paying attention when I was just talking about this a moment ago. All right, almost everybody's got an answer in here. Okay, so it looks like most people were paying attention. Yes, it's between room temperature and body temperature. So this means that sitting in your room, it will still be a solid, but if you hold it in your hand or put it in your mouth, that's going to help melt it. And that's one of the reasons why chocolate is so appealing, is that it does that melting in your mouth, and that gives it that really nice mouth feel and texture. You know, assuming that you like that kind of thing. There are a couple of people that I find crazy myself that don't like chocolate, but to each their own. Okay, so we'll get more into some of the reasons why there are these health effects once we get into later chapters, but I'll just introduce them now. So we talked about some differences between white chocolate and other kinds of chocolate. Apparently I'm scribbling all over here. Okay, so white chocolate doesn't have any cocoa solids, so it doesn't have the polyphenols in it, but it does have these fatty acids. So these are those long chains, and they've just kind of folded them around so that they're easier to see. But remember those zigzaggy lines, every corner is a carbon atom, right? And so all of these carbon atoms with no oxygens on it are going to be nonpolar. And usually this end isn't free like this. Usually it's attached to a glycerol. And so we don't really have those oxygens out there. If it were free like this, it would be an emulsifier, but really those oxygens are tied up so they don't really fire. So dark chocolate is the other extreme, where we have our all of the cocoa solids in there. And one of the most important ones is this theobromine. And we'll get into that more later, but theobromine is the chemical that's really bad for dogs. So median lethal dose for dogs is 300 milligrams per kilogram of body weight. So that means that your dog could probably have, you know, a chocolate chip or something, and that's not gonna be problematic for them. But you don't want them eating lots and lots of chocolate bars all the time. What happens is that this is something that both lowers the blood pressure, but also increases the heart rate. And so For us, our bodies process this chemical enough that it's what's called metabolism, but they process it enough that only a small percentage causes that to happen in our bodies. But dogs don't have that regulation, and neither do cats. But cats don't tend to try and eat chocolate the way dogs do. And so because of that, their hearts can just race too much. So I had a friend whose dog got into, they were going to go camping and make s'mores, and the dog got into some chocolate bars, and it was just for hours, just all over the house, hyper as can be and whatnot. So it didn't kill the dog, but it was definitely not good for the dog. And then it has some other chemicals in it. So this one, phenylethylamine is another chemical that's in there. These chemicals, and you don't have to memorize their shapes and you don't have to memorize their names or anything right now. But basically, these are the things that they said, these are why they say dark chocolate is good for you, because it has primarily these solids, sugar and fat. But when we go to milk chocolate, we reduce the amount of chocolate solids. So we went from 35% down to 20 to 30% and added in milk, and then usually some vanilla for flavoring as well. And so the milk is going to have more fats in it. It is going to give it a less sharp flavor, as I'm sure those of you who don't like dark chocolate know that there's a more smooth flavor for the milk chocolate. So those are some of the differences between the different kinds of chocolate, and that's why dark chocolate is usually the one they say is good for you. So good sides. It has antioxidants. Those are the chemicals that help protect us. Phenylethylamine is the feel-good chemical. So that's the one that makes you feel like you're having a good experience, kind of like in releasing endorphins in your brain that tells your brain, oh, this is a nice time. And then the theobromine, which is a stimulant and a vasodilator. So vaso is your blood vessels and dilator is expanding. And so that's why it lowers your blood pressure. The bad side of that is that we've got these saturated fats, and that chocolate candy is over 50% fat usually. And it's also very high in sugars. So generally, most people are trying to avoid one or both of fat and sugar. And so that's why not so great for us. All right, so theobromine was one of the chemicals I just talked about. This chemical is most associated with chocolate, but it is harmful to dogs and other animals. So why did I say that was? All right. So everybody was paying attention. Excellent. It increases their heart rate too much. Okay. All right. So I mentioned that chocolate also has ramifications outside of chemistry. So it's important to think of in a social context. We looked at the amount of chocolate that's eaten worldwide. And I pointed out that a lot of it is eaten in Europe and in the United States and in Australia. But that's not where chocolate is grown, where the cocoa tree is grown. So cocoa trees are only able to grow in tropical regions. So this blue band across the map here, that's considered the tropics. It's between the 23rd parallel north and the 23rd parallel south. And so this covers kind of the middle band of Africa, the northern part of South America. And so a lot of chocolate is grown kind of under this outcrop region of Africa in the Ivory Coast and in Nigeria and in Ghana. And a lot of it is grown in South America. So those were not places where people are eating tons and tons of chocolate. In fact, it includes many of the poorest and most vulnerable populations. So by vulnerable, I mean these are people that do not have the ability to resist exploitation, that somebody has control of the money or control of the power that keeps them from saying, hey, you need to pay me a fair wage, or hey, I need to have shorter working hours, or hey, you know, my kid's a kid and should not be exposed to chemicals, or should be in school. And so what happens is that the chocolate is sold to a broker. So this is a company that's sort of in between Hershey and the grower. So Hershey doesn't buy the chocolate directly from the place where they're growing the chocolate. They buy it from an intermediate. And so that broker is buying from farms all over the place. And they're not giving a lot of extra money to the growers. So the growers are barely making a profit at all. And so in order to make more of a profit, they pay their workers less. And what often happens is they will, this is particularly problematic in the Ivory Coast. They might kidnap kids and force them to work, or parents not having enough money to raise their kids and send them to school, because in many parts of the world, you have to pay to go to school. Their parents might say, okay, I want you to work on the chocolate plantation and send home the money that you grow. So the workers don't make very much money. A lot of times they're being forced to work. And a lot of times they're being exposed to a lot of pesticides to improve the growing. And they use very big, sharp knives to cut down the cocoa pods. And so those can be dangerous. So the people who are growing the chocolate are really put in kind of a dangerous situation. I'm going to skip this question for now because we're getting close to the end here. We haven't talked about balancing. Okay, I thought I had one more slide on that. Okay, so the good news of that is that very slowly over time, there have been some changes that companies like Hershey's and Cadbury and things like that have gotten into agreements where they're going to try and source their chocolate from companies that are what are called fair trade. So if you see fair trade on a label, that means that the chocolate is coming from a plantation where somebody has gone and verified there are no children working here, that the people are being paid a fair wage, that they're not being exploited. Sometimes it even means that they're making sure that the community is being developed so that children are required to go to school in that community rather than having that opportunity for the parents to send them somewhere to work. So it really is something that you can feel a little bit better about if you see fair trade on there. But very few companies, because of this broker situation, can guarantee that. It's pretty expensive. So when you see fair trade on a label, a lot of times it's from companies that are going to charge, instead of, you know, $1 for a chocolate bar, it might be $3 for a chocolate bar, because it's a lot more expensive to not only have that, but also to verify that that is true. I've noticed recently that Dove chocolate has started to have fair trade on some of their labels, not all of them. So the dark chocolate in particular. But most of the bigger companies haven't quite gotten there yet. But there is more and more of a push to try and get fair wages for people and to end some of the exploitation. All right, so sorry to end on such a downer there, but our big idea here is that we have this food that is very popular, that has a lot of chemistry that we can talk about. We can talk about polar and nonpolar. We can talk about crystallization. We can talk about health benefits of some of the chemicals in there, but it also connects back to other parts of your life. So those of you that are not chemistry majors, and that's the vast majority of you, are also going to see that some of those social issues that maybe you think about in some of your other classes, they are impacted by the foods that we eat. And I've brought chocolate to the forefront, but there are lots of other examples of things like palm oil, things like almond milk. All of those things have implications beyond just the chemistry of, is it good for my body? All right, so today we talked about, we did some review of calculating moles and molarity. We'll try and do that again on Monday, since it looks like we still need a little bit of help with that. We also talked about what's a saturated solution and a super saturated solution. We also talked about some of the different chemical aspects of chocolate. Any questions before we go? All right, so you are free to leave at this point. I will change the due date on homework 3 to Tuesday. I'll hang out here for a second in case somebody wants to ask a question.